Now we're ready for the main event. The crux of the class. The key components of this course begin right now with simple linear regression. Simple linear regression in general, again, one of the most widely used predictive analytic tools that's used in business, very applied, very flexible, very useful, considered computationally straightforward, at least what we'll deal with, which is technically the ordinary least squares method. So if we look at a business problem, right, and we have certain metrics, or what may be called a performance scorecard, we have certain metrics that we're keeping track of. And usually those certain metrics that we keep in track of are things that really have big impacts on our business, which is sometimes called key business drivers. And then we have KPIs, key performance indicators. And so we have this scorecard, or this collection of data. How did that become a key business driver? Is that indeed a key business driver? Is that a key performance indicator? I don't know. How did somebody pick this? Well, I don't know. Some guy picked it. Well, why should it be that, not something else? I don't know. Right? And so you want to avoid that. I mean, we just always did it that way. I got nothing. I don't know why it is that way. Well, this is where linear regression becomes important, because now we can connect those key business drivers, those key performance indicators, to firm performance. Whatever measure of firm performance that we're using. And so this is a very, very nice tool to justify what those key business drivers are, key performance indicators are, how they impact the business, and how improving those key business drivers and those key performance indicators would be expected to have on our business performance. And so get very, very useful tool. And then we can use those results, to begin a process of continual improvement. Hey, if we improve this key indicator, right? If we improve what goes into this key indicator, then we can expect this return on our investment. And it really it sets out sort of a priority scale as to where our focuses should be. Not just that this is important, but how important is it? That's very powerful. Right? That's very, very powerful. Okay, so in this particular unit, and these 5 fundamental facts or fundamental items here flow through us throughout our entire linear regression experience. So what we will learn a little bit about is what's called the simple linear regression model. Simple just means one x variable, one y variable, one independent variable, one dependent variable. Okay? Regression, that's just a fancy word for saying we're creating a line, we're creating a linear relationship. We use what's called the least squares method, and we'll see that a little bit. We're not really going to get too grunty in the calculation. When I took linear regression when I was a science student, you really got into the weeds of the calculations, and we won't do that. We'll stay in a purely applied frame of mind. But least squares method is the methodology we use to create our linear line. There are other regression methodologies, and hence why we just kind of bring to the fore the least squares method in case when you move beyond the hallowed halls of McEwen and you encounter this word and you go, well, we learned how to do regression, but I don't know what the least squares method is. Well, least squares was the method of regression that you learned. And so if you hear a different type of regression mentioned, that might be something that we didn't take in 312. Okay, coefficient of determination, that's going to tell us that very important metric to us, and you'll see this. This will be one of the one of the few things, I guess not many, one of the things that you'll see in midterm 1, midterm 2, and on the final. It says coefficient of determination, and it's just a nice, easy to interpret statistic that tells us how well our model is doing. We're going to have model assumptions. Model assumptions can sometimes feel theoretical, but they are very important because it tells us within what range or what universe our results are actually valid, that actually have real meaning. Because if those model assumptions are violated, we may get results. We may have a beautiful model. We may have very lovely numbers. But those numbers won't actually mean anything. They won't actually show the relationship properly. Well, that's pretty important, right? You don't want to be saying that there's this, and this relationship. It turns out maybe that's not right. Maybe no way, because you violated some of those model assumptions. So very, very important. And of course, you can't have a statistics unit without some testing, because testing is fun. And we still follow the same 6 steps to a statistical test that we will always follow. Very important. That statistical step structure that we learned when we reviewed hypothesis testing, it still applies here. Then we'll do lots of testing. So you can kind of see why that review of hypothesis testing was so important, because we're going to be doing lots of tests. Lots of tests. Everything gets tested. Everything gets evaluated, right? This is what an empirical approach to a problem is all about. It's all about testing and validation and objective measurements. There is judgment. I won't lie to you on that one. There is judgment, but we want to back that judgment up with, at least something somewhat objective, so that we're minimizing the bias. We'll never eliminate it. Let's not be delusional here, but we're trying to minimize that bias that every human has, myself included. Okay, so first step is we come to the realization we are making a model. And the whole point of a model is to simplify reality. Reality is very complicated. We're trying to take that reality and look at the key important bits that drive whatever it is that we're trying to measure. Right? So the reality is very complex, lots of intermingling, lots of moving parts. We're trying to simplify that reality. So yes, a model is a simplification. Okay, so some in academic circles, people go, well, I'm sorry, I really don't like that model. It's a simplification. Reality is far more complex. That model is really not that useful. Well, of course it's freaking simplified. It's the whole freaking whole idea of a damn model is to simplify the world so that it's somewhat understandable, and we try to predict it. And yes, we know that when we simplify the model, error is an inevitable result. Well, yeah, but at some point in time, you got to make a projection. You got to make a forecast. You have to know what you expect to happen in the future. Otherwise, how can you plan? How can you allocate resources effectively if you have no idea what the future is? Because you can't have that model because it's simplification. Well, what do you got to replace it with? Well, we are blah, 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 blah. Well, that's freaking useless, and that's probably why you're not in business. I won't say anymore without getting into trouble, especially since this is recorded. Okay, so yes, it's a simplification. Get over it. It's the whole point of it. So, regression. I love this because it's like it's so often the marketing guys get all the cool terms and get all the sexy slogans and stuff like that. So regression is a type of predictive analytics. Holy crap, does that sound cool, right? I love it. Predictive analytics. It means we're making a forecast what we think will happen based on certain factors. So certain factors, we can have a certain mix of factors, certain mix of, I'm going to call it, variables, where we have certain results for those variables, and then what would we expect our key performance indicator, usually sales or number of items sold or something like that, to be given this world that we think will exist, right? So regression is what we call a predictive tool. So that's really cool. There's lots involved when in this predictive analytics part. First of all, data, and for fear of stepping on toes. Hey, who's the data gatherers in a firm? Typically, your accountants, right? So the accountants are sort of the little oompa loompas of data management here. So we depend on our little oompa loompa accountants come up with our information. There's a mix of management objectives. Hey, you know what? This is what we want to look at. This is what we want to predict. There's information technology, of course, because this is all done on computer now. We'll do Excel, but we'll see a little tiny bit of a statistical program called R, which is very, very popular, mostly because it's open source. Little light on the user friendly, but very popular because its price is so attractive. And modeling, right? The old, good old stats, right? Bring it all together. So it's a lot of fun stuff. It really gets, when you look at the whole stats problem, it's really exciting because you have a lot of business issues to deal with. You have people issues to deal with. You have management objectives to deal with. You get to bring in a little bit of information technology. There's a little bit of math in here. So basically everything, right? You really have to be. Sometimes there's a sort of a misconception of stats as being just purely the number crunching. You got that person in the basement there in their computer, with 15 different energy drinks spread out across their desk and look like they haven't slept for 7 years and punching stuff out on the computer. And it's actually a little bit more diverse than that. So we're going to start off our journey into a regression by just looking at two variables. One dependent variable, which we'll call the y. That's the thing we're trying to predict. And one independent variable that we'll call the x. And that is that thing that we're using to predict that y. Obviously, we totally understand that there are likely to be more than one x variable, more than one independent variable. And we'll address that when we get into multiple linear regression. Right now, we just want to establish the basic relationships, the key statistics, the key interpretations from this model. That's easier to deal with when we've sort of streamlined what we're looking at, so we're not overwhelmed with a lot of output. Okay. So the other key thing that we need to sort of keep in mind is, so we still have that one independent variable, one dependent variable, but this is a linear relationship. So it is linear regression, so that relationship has to be from one to the other, has to be a linear relationship. Now, we do have tools available to us that will take that linear will take any relationship really, and view it as a linear relationship. Okay, so there are tools, logarithms, usually the most popular one, but there are all various transformations that you can do to take what's not a linear relationship and transform it into a linear relationship. So we just have to be aware of that there can be a degree of complexity is when we look at those relationships in a real world context. Sometimes they're not going to be as clean and well-behaved as the ones that we will deal with in a introduction to linear regression kind of class, okay? So just be aware. It's my public service announcement / disclaimer. Okay, so the dependent variable, that's the thing we're trying to explain. It's got a fancy word for it called an endogenous variable. Hey, statistics, we are consultants after all, and dependent variable just doesn't sound oomphy enough, doesn't sound techy enough, doesn't sound intimidating enough. Anybody can find the dependent variable, but boy, if I'm talking about an endogenous variable, I must have some big brain activity going on. So endogenous variables just means that's determined by the model. So the model predicts what the value of this variable is. Okay? We also see it called a criterion variable. I don't see that one too often, but you do see response variable, the y being described as a response variable. You see that used quite a bit. Okay, so the y being a response variable, being a dependent variable, being an endogenous variable, being a criterion variable. You'll see these synonyms happen quite a bit. So you just want to be aware of the language. It's all talking about the same thing. The dependent variable, that's the thing doing the explaining. We're using the values of that independent variable, We're using the values of that independent variable to predict or forecast what we think that dependent variable will be, or endogenous variable will be. X variable, again, it's got its own fancy name too. And its fancy name is called an exogenous variable. And X just means exterior, X outside the model. Right? So it's outside the model. And so it's determined outside the model, and then it's used to predict what the endogenous variable is. In another model, that exogenous variable can be turned into an endogenous variable. Okay, so sometimes we take the x's just for granted. Hey, they just appeared, but there could be a whole process into those particular variables, and this is where regression can get very complicated. We're going to make some assumptions on those x's that basically that they're what we call non-stochastic. They're not variable. They are a variable, but they are what they are. We're not trying to predict them. There are types of modeling where we may be predicting those x variables with a different model. So for instance, when I did my master's thesis in economics, I was predicting demand for electricity, and then one of my exogenous variables was itself some prediction that I used a different model to predict what those values would be, and then incorporated it into the main model. Okay, so it can get complicated depending on how the needs of the model really. Okay, sometimes this x variable is called a predictor variable. Okay, so it's got its synonyms as well. So we're going to have certain ways that we'll state these models. So there's population regression model, which is what what you see on the slide right now. There'll be population regression line, which is basically where we used regression to predict what that population regression model looks like. Then we will have a sample regression model, and then we will have a sample regression line. Again, line meaning the prediction. That would be our model, our calculation, whether it's on Excel or R or what have you. So a couple of things to note when you see the words population regression model. This is sort of the overall big picture of what it is that we're trying to look at. Okay, so this is something that one would see very early on in the process, often before data is even gathered. You sort of have an idea of what you're trying to predict. You have a y, and then factors, x, that you're using to predict that y. And we suspect, initially, that there is a relationship between that x and that y. The nature of that relationship is somewhat unknown. We just know that there is one. Right? So you see these Greek letters, beta 0 just means there's an intercept. The subscript 0 refers to intercepts. So we have a beta 0 plus some slope. So we think of our line in our previous experience with lines. We had y equals mx plus b. Well, b is a predictor for, or an estimate of, the intercept, which in this regression model is called beta 0. And m, right, in our previous experience, was the slope. Well, that's an actual number. That m is an estimate for beta 1, which is what we call the true relationship. Once we take numbers, we take a sample, we understand that our sample may not be perfect. It may not exactly be right. I mean, there's some random fluctuation. Perhaps there's a few observations in there that are atypical that could throw off our results. But there is sort of the truth. It's sort of a philosophical idea. There is the true relationship. Unknown to us, but it exists, that true relationship. And we're trying to predict what that true relationship is. And because it's unknown to us, you see the Greek letters represented of those items that are unknown. Right? You remember the saying, it's all Greek to me? One of the Basis for that is the fact that we have Greek letters here representing unknown parameters that exist, that are knowable, but just not known to us. Epsilon here looks kind of like a hockey net, represents error. Okay, so it's just a random variable representing error. Beta 0 and beta 1, we call those parameters. So when you see the word parameter, it's referring to those. Okay, so those parameters have particular meaning. They have very important business meaning to us. So our parameter, right, so we think of it interpretation-wise, and this becomes very important. The interpretation of the intercept is if x were equal to 0, so x is equal to 0, which means this beta 1 xi goes to 0, right? Then the average value of y is equal to whatever the value of that intercept is. So, for instance, we have y is weekly sales, x is the number of radio ads placed locally. Then, if we place no radio ads, right, x is equal to 0. If x is equal to 0, beta 1 times by x is equal to 0 as well. Okay? So we place no radio ads, then y becomes beta 0, and that beta 0 is the average weekly sales if no radio ads are placed. So for us, from a business perspective, it often has practical interpretive meaning, the intercept does, but not always. Sometimes it's nonsensical. Okay. Now, what about the slope? The slope gives us even more information, because usually this is the one we're really interested in too. We're even more interested in it. I mean, hey, what if we did nothing? What would sales be? That's a pretty important interpretation, right? Because then now you evaluate that against, okay, well, I gotta do up the ads, I gotta pay money, I gotta do all these radio ads, blah 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 blah. What if I didn't do anything? What happens then? Sometimes that's an important sort of benchmark to compare things to. And then we look and say, okay, what if we did place an ad? Right? And if we placed one ad, right? So X increases by 1 unit, we place one more ad. Well, how much would we expect? So that means like saying on average. How much would we expect sales to increase? Well, that's exactly the value of the slope, right? 1 times the value of the slope. If I go from 0 to 1, right? X was 0 before, so it's equal to 0. X is equal to 1 now. How much did it go up? How much did Y go up by? It goes up by whatever the value of that slope is. So the value in our radio ad and sales context is that beta 1 represents, I run one more ad. How much on average do I expect sales to increase? Now I can compare that to the cost and trouble of running an ad. Or maybe I'm running some ads already and I've already paid for the ad. That's a fixed cost, so we're not really worried about it. But then I can compare it to the variable cost of running one additional ad. So again, that slope gives us very, very important business meaning, right? X goes up by 1 more unit or goes down by 1 more unit, whatever. How much would we expect sales, or which is our Y, to change? Very, very important interpretation. The probabilities that I will ask you a question related to this very important interpretation in midterm 1 is 100%. In midterm 2 is 100%. And because there's a little regression model called a time series growth model that will appear in the final, the probability that you will see this again in the final is 100%. So something we really want to report. And some of it, this is some of the most important stuff that we get from the model in general, right? Is we start to see relationships and how much do those relationships impact, right? Because for instance, when we went, I'm just going to scroll real fast, don't get it, hopefully you don't have a seizure. Way back at the beginning, we're saying, hey, what are those key business drivers? What are those key performance indicators? How much do they impact our performance measure? Well, that's just looking at the interpretation of the slopes. Heck, that's the whole point. It's the whole point of objective measurement. It's the whole point of scorecards. It's the whole point of all of this stuff, right? It's the whole point of evaluations and objective measures is how do I interpret those slopes? I mean, if I can't do that, all falls apart. So it's like the key glue holding it all together. Okay, I'm going to flip really quickly again and hopefully don't cause you to have a seizure. Okay, now there's that last guy there, the random error, the unsung hero. Nobody likes to talk about it, but three things that sort of drive that random error. First and biggest thing is we're missing variables. So, and this can be big. This can be big, especially with simple linear regression, and we'll do a simple linear regression example. We'll do a couple of them actually, and you'll see, okay, yeah, I can see that error's coming from, because you know what? This, and this would also impact sales. And, you know, that impact, that though the sort of the contribution of those variables or those omitted variables, their effect, it shows up somewhere, right? If they're a legitimate independent variable, they don't just disappear. Their impact is felt somewhere, and if it's not felt in the model with the slopes, it's going to be impacted in the error calculation, because their impact it shows up somewhere. Okay, so big source of error is omitted independent variables. Second source of error is measurement error. You know, you got the intern punching stuff in the data, getting a little bleary-eyed, getting a little tired, you know, punches in a 5 instead of a 2. I mean, this is something I do all the time. I'm guilty of measurement error. I'll look at something and I'll have one number, and right below it'll be another number, and you know, I've got my stigmatism on the eyes, and I'll write the number down that's below it instead of the one above it. And you know, these things happen, right? It's the human aspect of it, and sometimes there's just the measurement error. Sometimes there's the non-human aspect of measurement error, is that our tools just can only measure, you know, the tool that we're using to measure, whatever that tool happens to be, has a degree of precision to it, and that is just what it is, right? And it's subject to a little bit of variability as well, right? I deal with a lot of electronics measurements and using lasers to measure things in the air, I guess, for lack of a better term. And those are very precise, but they're not perfectly precise. And there is a little bit of an error, because often we're measuring something that's related to something else, because we can't measure the thing itself directly. And this happens a lot in business as well, not just in science. And so when we do that, there's always a scope for measurement error. And then there's just the old-fashioned random error. There are just some things we just can't quantify. Right? Tastes are the biggest ones. I like the color blue. Can you quantify that? No. I like blue. I mean, no. How do you model it? How do you like the fact that I like blue? You can't, right? They're non-quantifiable factors, and those become important because, and it can be things related to. I mean, you see this a lot in technology. It's really hard to focus group for customers, because you know, when you're looking at that next new thing, clearly people don't know what that next new thing is. But you come up with that next new thing, the iPhone, for instance, and people go, whoa, gotta have it, right? But how would you have known? You wouldn't have, right? It's just random, hey, this just fits. It just is this way. Okay, next clip, we'll talk about sample regression models.